Hello and welcome to the Energy Resilience Lab. Our lab is dedicated to giving you the knowledge, skills, and encouragement you need to become more energy resilient and to start you on your path to energy independence. Our show consists of 4 formats. The first one's informational, second is interview style, third is news, so that can be news related to issues that are happening around us that we can become more resilient to. Or it can be news related to new technologies that are becoming available and becoming viable for us. And then the last is question and answer. So thank you for watching today, and please like and subscribe to this video. And in addition to that, please add any comments or questions that you have on the videos. I will read them and we will answer those questions on shows that are dedicated to question and answer. Today I'd like to introduce you to a small solar panel. I think this will be helpful because you'll understand how it works and the different problems that can arise with portable power systems as well as larger systems that may be on your home or industrial space or even going to the utility scale. So today this is a 12-volt folding panel. Some of the things we need to learn about solar cells is that they are current elements. So the start of any solar cell description should start with how it works. So the solar cell is a silicon wafer that's been doped to provide current when photons hit it. So when the solar energy from the sun hits this solar panel, there's actually 36 cells in this panel here, but each little solar cell, the first one being this one here, provides a little bit of voltage and then usually a significant amount of current. So this is a single solar cell that would be used in a industrial or commercial panel. Kind of the older style panels would be full solar cells like this size. But as we've went to higher and higher voltages to get higher efficiencies and more energy out of the solar arrays, we slice them up and we add different systems to optimize them. But just going with this one, this whole panel is a series of cells. So this individual cell, if you were to cover this up, it would kill the efficiency of this panel. The current through this panel is limited by the solar cell that is providing the smallest amount of current. So when you have a series circuit, the series circuit always has to have the same current. And so this whole panel is a 12-volt panel. And when I say 12 volts, it's more talking about what the battery system would be that this panel would charge. The actual voltage of this panel for maximum power is around 18 volts DC. So solar hits the panel, it starts providing current. This half of the panel provides around 2.75 amps. So if you combine the two sides of this folding solar panel, you get around 5.5 amp. That is at max power, but that's how the solar panel is working. The sun is hitting it, the photons are displacing the electrons are running along the bus bars in the panel, and that power is then transmitted to your final plug that goes into your power unit, or in larger scale systems you would series these panels and build the voltage higher and higher to match your system voltage that you need. When you're using a portable panel, you should never put these in series. Solar panels can be dangerous. As you stack them in series, if the voltage is leaking to the grounding portion of the panel, it can be high enough that it can be lethal. So it's best if you have a portable panel to not do those in series. Anything above 60 volts is kind of the lethal limit. So if someone did want to stack them a little bit, you just don't want to go past the 60 volts. But in general, I would just avoid it because you need to get solar panels that are rated to be put in series. With that, we can kind of break it down. So this little section right here is providing about a half a volt to 0.6 volts at maximum power. And there is 36 of them in this pane of the foldable solar panel. The main concerns with solar panels is that you need to get a symmetric amount of solar energy onto the panel. So if your panel does get dirty in a small section, you're going to need to clean that often, because it's going to limit this whole portion. So this side of the panel provides 50 watts of power in full sun at the perfect angle. Having even just one solar cell covered with dirt or mud or grass will cause this panel to produce way less. Just anecdotally, when I've been working with these panels, having one solar cell covered would limit it by like 90%. So you're looking at a 5-watt panel if you just have one section covered. So it is nice to have 2 panels that are both 12 volt in parallel with a small solar energy storage system, because this one pane can get covered a little bit and the other one will still provide the full power. But in general, we just want to clean it and get it as clean as possible to provide the amount of power that it is rated to provide. So to go through the characteristics of this panel, there's an open circuit voltage. Open circuit voltage is referring to the amount of voltage that this panel makes when there's no current flowing. So when you have an energy storage system and it gets to be full, the charge controller needs to block the power from the solar system because there's not enough room in the battery. So it can use it to power devices and things with the load that's going through it instantaneously, so at each point of time, but it can't add any more to the battery, so it has to limit how much power is getting into your system. So when it totally isolates and stops taking power, the solar panel will go to its open circuit voltage. And so that just means nothing's connected, there's no load on it. And so in this case, this one is around 21 volts is the open circuit voltage. So why that is important is because when you build a system and you have a maximum power point tracker or you have a PWM charge controller, it needs to be rated high enough that it can block the maximum voltage that this solar panel can produce. In larger systems, you'll stack them in series, so you have to add up the open circuit voltage, but that is the reason we need to know what that value is. The next value is the maximum power voltage and current. So when you are drawing power from the solar panel, so your energy storage system has room in the battery and it's covering its load, the panel is going to provide, so given that you've set it up and faced it directly at the sun, it will give you its maximum power. So in this case, this is a 50-watt panel here, so it's like 2.7 amps gives you the 50 watts of power. So that is the maximum power. And then the last one that's critical is the short circuit current. So when you have a solar panel, the opposite end of the spectrum, so when you're not taking any power, that is the open circuit voltage. But if you're taking all of the power, so in case you actually short the ends of the solar panel together, the power side, so plus and minus together, the solar panel will provide current, and that will be the maximum current it can provide. That is the short circuit current. And so in this, so one panel, because that's what we've been kind of limiting it to, it's around 3.3 amps. So the maximum power current is about 2.75 amps, and then the maximum short circuit current is 3.3, so you can see it's a little bit higher on the short circuit current. Things to know about that is that the short circuit current is not valuable to us. If you have a short circuit condition, you're just losing all of that energy within the solar cells themselves anyway. So you're just making current and it's just all getting burned up in the internal resistance of the system. That energy isn't getting used anywhere, so you're just chasing your tail essentially. And so what we want to do is actually get to the maximum power voltage and current of the solar panel. But one of the problems that arise is that just due to the conditions, just due to how cloudy it is or how sunny it is, the amount of power that you get from the solar panel is different. And so when you have a PWM controller, it's going to be trying to maximize something, so it'll try and maximize the amount of current you're getting from your solar panel. With an MPPT controller, the power that it's bringing in from your solar panel can be, not the power, but more so the current and voltage can be adjusted by the charge controller drawing more current or slowing down the current. So it's continuously checking and adjusting the amount of current it's taking to get a maximum. So that's why we call it the maximum power point tracker charging system, I guess. The limitations of the solar panel are that if you have to keep it clean and you have to make sure you keep it pointed at the sun. If you just point it a certain direction, so you just point it south at a certain angle, you will get power throughout the day, but it's going to taper the whole day. So there will be some point when you get the maximum power from your solar panel, but the rest of the day, it's usually around 5 hours, 5 to 7 hours of sun. You'll get just a portion of the power throughout pretty much the whole day, except for right when the sun is facing directly at it. So if we want to compare how much energy you're getting, a PWM controller, charge controller will get you a certain amount of power, and then moving to an MPPT charge controller, you'll get about 30% more. And then if you have an MPPT and you have solar sun tracking, essentially where the solar panel is actually moving, following the sun, that'll give you another boost of about 30%. So if we're maximizing it, we would need to get a maximum power point tracker as our charge controller, and we would have to have the solar panels follow the sun throughout the day. The rule of thumb for how much energy you'll get from a solar panel, so this combined is 100 watts. You'll usually get around 3 to 5 times the rated solar panel power in energy. So in this case, it's a 100 watt solar panel, so you're getting 300 to 500 watt hours per day. And if we look back at one of our earlier question and answer episodes, the deep freezer that we analyzed used about 400 watt hours per day. And so one 100 watt solar panel should cover a deep freeze for a day. That's assuming that you're always going to have sun, and that is not always the case. So that's the problems with some of these renewable options, is that you don't get sun for a long period of time. So in the area I live, we'll get 3 or 5 day storms, and in that case you have to have enough energy to cover whatever system you're trying to run. Refilling of your system will come at between 3 and 5 times the rated solar power of your solar panel. So that gives you an idea of how it works and kind of a couple of the limitations that come with it. If you guys have any questions or you'd like to know more about these systems, that would be great. This was a 12 volt panel, so we have 36 cells on this panel and 36 on that panel. That's why we got the maximum power voltage of 18 volts approximately. And then in the same configuration, if you just stack these two panels together, then you get a 24 volt solar panel, and so it's 100 watt 24 volt. But when you do that, what you're going to find is that if you cover any of the solar cells, you lose efficiency for the whole panel. So it becomes more and more critical that you use that you clean it, and that you face the system towards the sun. This is the first of a series of solar shows that we're putting together. This first one is the portable. The next one is talking more about home energy storage systems and home solar systems and how the solar systems work. Then we'll go into industrial and then utility scale systems to give you kind of the full overview of how solar works for us in the field. So thanks for watching. Please like and subscribe and add your comments and questions at the end. We'd love to answer your questions with regards to solar and anything else that you have for us. So thank you and have a great day. We'll talk to you guys later. See ya.